Hello, and thank you for joining the Traceable webinar, what AI can do for your APIs. We will start in a couple of minutes. Let's let the other attendees join as well. Bear with us. All right, let's get started. Thanks again for joining. Today, I want to introduce two of Traceable biggest experts on machine learning. I know I learn a lot from them. Please welcome Ravindra Gunter and Ranaji Krishna. Ravi, the floor is yours.
Yeah, thanks, Renata. Thank you all for joining this webinar on applications of machine learning in API security. I hope you'll find some of our arguments convincing, and the information that we're going to share, I hope it's going to be interesting to all of you. So today I'm joined with my colleague Ranaji Krishna. So myself and Ranaji, we work on machine learning algorithms, and we strive hard to take machine learning algorithms to production. We look at practical approaches to solve some API security issues using machine learning. So what I'll do today is the presentation is actually split into two parts. In the first part, I'll be talking about how some of the challenges, what are some of the challenges for machine learning in API security. And I'll briefly cover two use cases involving user behavior and risk. And then I'll hand it off to Ranaji, who's going to walk us through API metric anomalies. So before we get into API security and machine learning, maybe we should just take a step back and see what are the challenges we're going to face when we apply machine learning to this field of API security. For that, we could actually start with the supervised learning approaches. So in a typical supervised approach, what we would do is we would either build rules. So you could look at regular expressions as a supervised approach. Or you could build a model using a machine learning algorithm. But the key is the data that drives these machine learning algorithms, or the data that governs how we build these rules, comes from observing successful attacks. So only when you see successful attacks, we come to know how these attacks take place. We understand the data, and then we go ahead and build models. So then once we have these models, we go and deploy these models in order to prevent the same attack from occurring. So that's the key. The key is the same attack or slight variations to the attack as generalized with the model can be detected by supervised learning approaches. But the catch is this kind of an approach works when we have similar environments. So what I mean by similar environments is, so imagine you have 100,000 machines running a particular version of an operating system. And there is a particular attack which takes place on one of the versions of the operating systems. We found the attack, we found the attack patterns, we created the rules, or we trained the model, and we deploy the model. So once you deploy the model, you are guaranteed to protect the remaining, let's say 100,000 machines from, you can protect the remaining 100,000 machines from the same attack, because now you have a model which generalizes across the environment. It works because all the remaining machines are running the same version of the operating system. But when we look at API-driven applications, we see a completely different pattern. The attacks expose a very different attack surface, because of which most of the vulnerabilities are business logic abuses. Now, to a stateless detection system, these attacks look like genuine API calls. But in reality, business logic abuse is a combination of API calls. The way you call the APIs, the way you transfer data between APIs, that's what results in the abuse of the API ecosystem. And stateless systems cannot catch these kinds of attacks. Now, the other aspect which you see in case of API-driven applications is we don't have this similar environment which we easily had in the case of in the example which I gave. So let's take an example here as well. Imagine you have two e-commerce sites, and you know that all e-commerce sites support a shopping cart, right? So given these two sites, if you visit these two sites, you would probably experience the same business logic. You are going to add an item to the cart, you're going to check it out, then you're going to make a payment, and then the transaction is done. But what is the difference between these two sites is the way the APIs are wired together. So each site would implement a different set of APIs. They have a different API spec. The logic is split across different APIs in a very different fashion. So what that means is even if you do detect an attack in one of these sites, it's going to be very hard for you to detect the same on the second site because the environments are different. The third aspect is getting supervised data is virtually going to be very hard in the case of API security because these environments are varying. Now, coming back to where the state of the art is, we all agree that, at least I feel that attacks are very difficult to craft. It's not that attackers can just craft an attack and they can get into any system. And the defenses definitely are difficult to build. So if you talk to any of your pen testers or anybody participating in bug bounty programs, you'll see that they spend hours or sometimes even days trying to get into the system, but still they're not able to get in. That's because there is a lot of maturity which has come in terms of how we are building applications, how we're deploying applications, what are the best engineering practices that we're following, and so on. In addition to that, we have widespread adoption of defensive schemes such as multi-factor authentication or using RBAC. So what has actually happened is the barrier to entry has increased for the attacker, and the expectation from defenses has also gone up. Now, given this scenario or this situation that we are in, we need to look at how machine learning can contribute to solving API security issues. Now, there is a lot of hype around machine learning. We know that it's an era where we have algorithms that process data have just risen to the forefront. But the reality is, in the case of API security, these algorithms now need to learn separately for each customer environment. They need to adapt to the data that you find in different customer environments. You can't just use techniques like transfer learning. You can't say we are going to learn and train a model in one place and use it in another place. It's just not going to work. In addition to all of this, we also have concerns related to privacy and regulation. So a lot of cases, you will see that the regulations are so stringent that the machine learning algorithms which are data hungry don't get quality data. And you need to adapt these algorithms to survive in this kind of a constrained situation. Now, given this brief background to what we see as the challenges to machine learning, let's look at what the attack surface looks like. So I'm going to present the attack surface from the point of view of a machine learning algorithm implementation. So in the case of API security, the way Traceable is dealing with APIs and providing us with API security, we see 4 or 5 different entities in action. So at one end of the spectrum, you have users. These are the ones who trigger actions with APIs. Then we have what we call as edge APIs. Edge APIs are the entry points into the business logic. Within the boundaries of the edge API, right behind them, you have what we call as internal APIs. So internal APIs could cascade into a large number of APIs, which eventually takes us to resources. Sometimes they could even lead us to third-party APIs. Now, the glue between all these is the API interaction, and you naturally have data flowing through right from the users to the resource and all the way back. The common question that any machine learning professional would ask for is like, what does your feature look like? What's the feature vector? What's the characteristic of your data? Now, let's look at users. So users is basically, you could look at users as a nested JSON object, very rich in information. There are lots of different types of information that you can associate a user with. The interesting part here is this data is highly categorical in nature. Either it's categorical or it's ordinal. The amount of numerical data that you find is pretty less. So any technique which would try to map this into a vector space, try to map this into a tensor, is going to is going to bloat up in the memory consumption, in the computational cost, and so on. So this is something that we need to take into account when you're dealing with this high dimensional categorical data. The next aspect is the APIs themselves. So the interaction between APIs can be considered as a graph. I'll show you an example of what the real world API interaction look like. But for this slide, you could look at the API interaction as a graph. Each of the green nodes you're seeing there is an API, and then you have edges connecting those APIs. And the APIs are connected because there is data flowing between one API and the other. Now, on the edge itself, we have the API definition. You have the path of the API, the query parameters, the request header, the response body, the request body, and so on. So this again is a very rich source of information, and it's a rich source of rich source for feature extraction. Now, when you go deeper into the API, you have the actual logic. It's basically code. And the code itself is another dimension of information for us to consider. And at the end, you have the resource. You can simplify the resource to be some kind of a database which has information very specific to each of the users. So it's not API specific, but it could be user specific. So that's the key difference that you would see in this. So given this landscape of data that we have, now we need to see how we can utilize this information to power various features in your API security product. So before we look at the two use cases, let's look at some of the challenges and how we can address these issues. So APIs and environments vary from customer to customer. So which means supervised learning has very limited role to play in this scenario. Attacks don't look the same in all environments because it depends on how the APIs are wired. So what we propose is, in fact, this is what we do. We focus extensively on unsupervised and self-supervised flavors of machine learning. Now, information itself is hidden within the API definition and the API interaction. So this interaction looks like really large graphs with very dense link level metadata. So naturally, if you're dealing with graphs, you have to deal with scale. And in security applications, we have the additional constraint of detecting a vulnerability within a very small time deadline. And graphs are notorious for being computationally intensive. So we need to come up with very smart algorithms that look at graphs differently. We cannot fixate ourselves on theoretical aspect of graphs. So we'll have to break down some very nice graph formulations into sometimes hacky solutions. Sometimes we come up with our own approaches to simplify how we can use graphs. And finally, we have this complex matrix of users, APIs, data, and resources. And it has a tremendous combinatorial complexity. The only way to handle this in your application is to approach it with a divide and conquer mindset. So let's look at what API interaction would look like. So here, what you're seeing is two graphs. These the black bars which you're seeing are nothing but APIs, and the links which you're seeing are data flowing between different APIs. What you see here is the user behavior. So what exactly is user behavior? Now we talked a lot about APIs, and we talked about APIs interacting with one another, right? Now, the APIs interact with one another only when users trigger an application business logic. So only when you ask the APIs for certain data, you give them certain data and ask for a data, that's when the whole API interaction is made visible. For the user looking at it, it's all transparent. But when the machine looks at this API interaction, this is what the machine sees. It sees a very complex graph. So you'll see a lot of patterns in this graph. You'll see the presence of curved vertices. So these are vertices when you delete, the graph becomes disjoint and hence your application fails to function. Then you'll see certain vertices which are critical in the sense there's a lot of data flowing through those vertices. You can see patterns of merging and splitting, which is a very special characteristic of the way the API has been implemented. And you'll also see in some cases, in the second graph here, you'll see some kind of a tree kind of a structure for the implementation. So what this is basically telling you is there are two different implementations here, and the two implementations look very different. And we need to handle these kinds of complex graphs when we're looking at the behaviors of what users are doing within your environment. So we talked about business logic abuse. So what is the difference between behavior and business logic abuse or business logic? Now, business logic is something that end users experience from the application. But user behavior is a subset of the business logic, which is very specific to a particular behavior, which is observed. So the key here is to be able to observe. What you observe, what you observe for a particular user becomes the user behavior. What you finally see out of the application is the business logic. From a machine learning point of view, it is very difficult to capture business logic. What we can do is we can capture business logic in the context of a particular user's behavior. So that's the only way we can solve the business logic abuse. Because it's a data-driven approach, it's not a rule-based approach. You cannot specify the business logic. When you have hundreds of APIs, nobody can really tell you how exactly those APIs are wired. So machines need to figure these things out from the data. So in our mind, we feel business logic and user behavior are two faces of the same coin. And the user behavior or business logic is a complex graph of API calls that you have already seen. In typical applications, you'll have hundreds of API calls, but you're going to have tens of thousands of users making use of these API calls. And the way the users call these APIs, again, creates different virtual notions of what the business logic is. So if you have, let's say, 100 APIs and all the users are using, let's say, a mobile app, and the mobile app has, let's say, 4 or 5 buttons which the user can press. So what the app is doing is it is constraining what the user can do with these APIs. And on the other end, suppose these APIs were made open and you could access these APIs via API keys and you could write your own Python script, then the way these APIs would be used would be completely different. So the same set of APIs would look different in terms of the way they're behaving for the set of users who are using these mobile apps. But the same APIs would look very different for people who are using Python-based scripts to access these APIs. And the other aspect that we have observed is these API call sequences can be really long lasting. So there are call sequences which last for days. So this adds a kind of complexity to our representation. It adds memory complexity, it adds storage complexity. So we need to address all of this when we are looking at user behavior and abuses to user behavior, which eventually leads us to business logic abuse. So in our implementation, we have one feature which is currently released as a beta feature. So where we try to capture business logic abuse in terms of user behavior variations. And it's all completely driven by the usage of these graphs. So the way we have built it is we take traces and then we go through a graph representation. The graph representation is not a very standard representation where you have nodes and vertices and you have structures for nodes, structures for vertices and so on. We have a very simple representation which is more like embeddings, so which makes our graph processing much faster. Once we have this graph representation, then we apply a bunch of algorithms on it. We use graph similarity algorithms, we use clustering algorithms, and we also use partitioning algorithms. And using these algorithms, we come up with different flavors of behaviors. We say we can identify outlier behaviors, we can discover bots, we can discover behaviors which we think are risky, and we can also show what is the typical or the normal behavior of regular users in a system. We surface all these behaviors in a user interface, which looks like this. In this interface, you have the behavior classification here in the center. And then we have something called as group statistics. So the behaviors today are classified into 4 classes. We have an attack behavior, a normal behavior, outlier behavior, and bot behavior. Some of these behaviors have a subtype. So for example, a bot behavior tells you what kind of bot it is. An attack behavior tells you what kind of attack we are seeing. These attacks are also available to us through our detection engine, which is a very sophisticated approach to detect API vulnerabilities at an API level. We detect spec anomalies, we detect patterns of violation in the data, and based on all of that, we discover some of these vulnerabilities. And we also have outliers, which basically shows you behaviors which are like very distinct from the normal behaviors. Now, in the group statistics, we show you how many users fall into this particular group. So let's take one case. Let's take, we have an attack. So what this thing says is there are 2 users who have exactly the same API call sequence, and they have apparently performed the same attack, and that's why these 2 users fall into the same group. But then how many sessions did we see? We saw 3 sessions. And how many different APIs were called? There were 10 different APIs that were called. And what was the median duration of the session? How long did the sessions last? So it's like 262 seconds. That was the duration of the session. In addition to showing these gross statistics for these groups of users or the behaviors of users, we also have the scheme where we kind of tag those clusters using a label. In some cases, it's very difficult to generate a label, but where we can, we use a natural language processing approach, which uses the API names and combines those API names to come up with a single word or sometimes a single phrase tag for these clusters. Now let's dig deeper here. So if you click into the behavior, so I've taken a screen grab where I've checked the attack behavior here. So when I click on the attack behavior, you will see exactly what the attack looks like. So you will see the calls, the APIs that were called by all the users in this group. You will see the API that was actually attacked. And we also know what APIs preceded the attacked API. So we know how the attacker got in here, what the attacker did before the attacker eventually came to this API to attack. We also have other information such as a histogram. We can see, so if you look at this graph, we have eliminated loops. We don't know how many times each of these APIs were called. Though sometimes what happens is these APIs are called repeated in a loop. It's very cumbersome to show you all of that in this visual. So what we do is we break that up and show you in the form of a histogram. So we know now how many times. So we see here, this particular API was called 4 times. And out of the 4 times, at least 1 time, there was an attempted attack here. And the attack was an authorization bypass, or it's a BOLA as per OWASP API top 10. Now, dig deeper, we'll know who were the attackers. So in this case, there were 2, the fact that you're seeing email IDs means these are authenticated users. So there are 2 users who performed the same attack. Now, there are cases where that happens. Some of the cases that we have seen is we have automatons running in different locations, and the automatons are attempting the same attack sequence. When that happens, the behavior is the same, and then these 2 users get grouped into the same behavior group. We can also perform actionable things on this. Like, for example, you could say block and watch this entire group of users. We don't have this feature today in our product. We are yet to build it. That's why I've just graded it out. But rest of it, you can actually see the rest of it as in our as the beta feature in our product. So going deeper, one of the requirements is to understand how the attacker behavior is different from the normal behavior. So in the previous slide, we saw where the attack took place, what was the API called before the attack, and so on. But it is also of interest to see how it is different from the regular behavior of users. So we talked about graphs, right? So it's very difficult for human analysts to compare these graphs. So we have algorithmic implementations which will process these graphs and give you the exact graph which is the closest normal behavior to this attack behavior. We can also point out areas where the graphs match. And what I've done here is I've shown you a perimeter around this around this particular API. So the reason why I've shown you this perimeter is you could basically use these graphs to decide what APIs need protection or what APIs need extra protection. You could also decide what APIs need to be escalated to your product dev teams for them to take a closer look so that they can plug this path from leading from this API onto this API. So it's some kind of a shift left where you tell your dev teams that we have observed this, this is how the APIs have been wired, and this is where we saw the attack. In most cases, what happens is the development teams work in isolation. So each team owns a certain set of APIs. They understand those APIs very well. They protect those APIs well with good programming practices. But when the bigger application is built, these APIs which come from two different engineering teams are put together to build your application. So they really don't know how their APIs are being used. So the other way you could use this visual is to tell them exactly how the users eventually end up using your APIs. And this is an insight into improving the complexity or reducing the complexity of your application. So if you have a lot of cut vertices, if you have a lot of nodes in the graph where you have merges and then splits, then you could actually simplify your implementations in those nodes. So it helps them bring about efficiency in the system as well. Yeah, so this is what we have in terms of user behaviors and business logic, visualizing business logic. Next, I will go into a couple of other items related to risk. We have what we call as API risk. API risk is basically a quantification for how important a particular API is in terms of the vulnerability that it could expose. So we look at various characteristics of an API. We look at what goes into the API, what goes out of the API, the inputs and the response from the API. We also look at the origin of traffic to the API. Where are the users coming in from? And we also look at activity. How many times a particular API is used by which class of users and why are they using it? We also look at whether the API is external facing, whether it's an internal API, whether the API is authenticated or not. And combining these three different dimensions of an API, we produce what we call as the risk score. Risk score can be used in multiple ways. You could basically use it to draw perimeters. You could draw perimeters around APIs which have high risk. You could actually feed in the risk score to false positive reduction engine. You could have the granular perimeter which I just talked about. You could trigger additional detection logic on these specific APIs. Even if you have mildly suspicious behavior, you could actually escalate them. And you could also pass this information of API risk to a new approach to security called the plausibility models, which I will talk later on. So, so, so we covered user behaviors, which is the interaction between APIs. Now we looked at API itself in terms of API risk. Now we look at the other aspect, which is the user. So under users, we are building this option called the user trust. So what's the difference between trust and risk? So risk is something which you estimate, whereas trust is something that you build by observing data. So in case of users, we have this option to observe the user behaviors over extended periods of time. And because of that, based on the behavioral patterns, we're able to assign each user a trust score. Now, similar to API risk, we have multiple dimensions on which we evaluate the user. We evaluate the user on the behaviors, whether they were attacker behaviors, outlier behaviors, did they fall into a cluster where there were bots, and so on. We also look at what kind of APIs these users have been repeatedly calling. We look at the origin, where did the users come from, whether those IP addresses have poor reputation or not. Are they coming in from completely different countries? So these kinds of features are used into computing the user trust score. So once we compute the trust score, we qualify the user on three dimensions. One is the identity, the second is repeatability, and then the third one is familiarity. And based on the quantification, we feed in the outputs to our detection engines, such as detection of ATO, detection of suspicious activity of some specific users, or even into a false positive, false negative reduction engine. And again, the same user trust can go into our plausibility models as well. So coming to plausibility models, let's see. Yeah. So plausibility is a kind of vision that we have in terms of API security. So if you look at most of the API security approaches we have today, they're all detection based, but we are keen on getting into a preemptive threat detection approach. So in a preemptive approach, what our vision is, we should be able to figure out an evolving threat before it gets critical. Now, how do we do that? One of the ideas that we have, which you're pursuing, because we have the data, we have the intermediate steps, which we've already built, is to use model-based reinforcement learning as a paradigm to create unobserved threat scenarios. If you are familiar with reinforcement learning literature, you will know that there are model-driven and model-free approaches. Model-free approaches are highly theoretical and they're not practical in real world. But model-driven approaches create kind of reduce the scope of the problem, because of which it becomes more tractable. And because we are able to discover the business logic, we are also able to define the environment. So in most cases in reinforcement learning applications, the environment is undefined, and the automaton figures the environment out by exploring the environment. And in security applications, you don't have the leisure or luxury of exploring an environment. So the environment needs to be constrained. And thanks to the tracing platform that we have, and thanks to the fact that we can build these user behavior models, we are able to kind of create that environment within which the automaton can figure out these unobserved scenarios. So what we're going to do is we will be combining the API risk and the user trust along with our behavior models. I feed it into a reinforcement learning framework, and the output of that is going to be, imagine the reinforcement learning framework thinking about what are the possible attacks, thinking about the various paths that can lead to a particular attack. So it's kind of an imagination, a machine-driven imagination, and it's going to create these graphs which will tell you possible attack scenarios. So these scenarios are generated by the model; they are not observed. And once you see a threat actor following any of these paths, you know for sure that this is a risky behavior, and we can flag that even before it can reach the criticality. Yeah, so this is like a very quick summary of some of the work that we have been doing in terms of risk, in terms of behaviors, and in terms of plausibility. I'll be happy to answer any questions. You could post them on the channel. But right now, I'll hand it off to my colleague Ranaji, and he's going to talk to you about anomaly detection in API metrics. So let me stop sharing. Ranaji, you can take over.
Thank you, Ravi. This was very insightful. And as Ravi said, there is a Q&A icon at the bottom of your screen. Please feel free to type in your questions, and at the end of the discussion, we will be happy to answer.
Okay, thank you, Ravi, for that. Hello, everybody. My name is Ranaji Krishna, and I'm a data scientist at Traceable. Today, I'll be talking about one of the problems that we've been working on, which is anomaly detection in API metrics in order to assess the health of service in our customer's environment. So I'd like to start by painting a bigger picture and then getting into the details. So at Traceable, essentially what we see our customer service is that it comprises of APIs. And we use metrics such as response times or number of errors to get an idea of the health of that service. What we essentially do is at the API level, we track how these metrics perform across time, and then we detect anomalies in these metrics. And in order to do so, we predict the value of the metric in the near future. So let's say, for example, we predict what the value of this particular metric for this particular API should be in the next 5 minutes. And then as the real value of the metric comes in, we compare it to the predicted metric. Now, if the difference in value between the predicted and the actual metric value is large, we highlight it as an anomaly. If it's not large, then we say that it's not an anomalous data point. And then what we do is we aggregate these anomalies across the APIs to the service level. For example, if there are a lot of APIs experiencing anomalies, then we surface it at the service level as an anomaly. Or for example, if there's an API or a bunch of APIs showing very high level of anomaly, the difference between actual and predicted is very high, then we surface that to the service level as well. So in just, this is what we do. I will now go down into the details. And for that purpose, I've broken down the talk into these following subtopics. So let's get right into it. So as I mentioned, the objective is to assess the health of the service in our customer's environment. And we do this by doing a couple of things. We detect anomalies at the service level. We also identify which APIs are causing any of the anomalies that are experienced at the service level. And we further try and forecast what the metric value should look into the near future for that particular service. So as I mentioned again earlier, we see that the customer's environment comprises of services, and each service is made up of a bunch of APIs. And the health of a service is determined by the performance of the underlying APIs. And in turn, the performance is measured through metrics that we have understood as important metrics or key metrics. In our case, we use the response time, the number of errors, and the number of calls to assess the health of the API. This is somewhat similar to assessing the health of, let's say, a human being. We would look at, for example, the weight of the human being, his or her blood pressure, or what stress level he experiences, in order to get an understanding of how healthy this human being is. So these are the kind of metrics we look into the API world to get a sense of how the API is performing. We then aggregate these metrics across the APIs to the service level. And an aggregation could be something as simple as taking the mean across the APIs at that certain time interval. What this diagram shows is that these values at the service level for a particular metric, response time in this case, is essentially a mean of what we are experiencing at the API level across all of the APIs. Anomalies are identified at the service level if a lot of APIs are experiencing anomalies within the service, or if some APIs are experiencing a very high degree of anomaly. And the reason we don't surface every anomaly at the API to the service level is simply to reduce noise. At any point in time, some API may be experiencing some form of an anomaly due to some network caching or slow traffic coming from other APIs. We don't want to service it as an anomaly at the service level. The repercussion of servicing anomalies at the service level is that it makes a call to an analyst who has to go and dig into what is happening. So we want to decrease the noisy alerts and make it more meaningful. I wanted to add some face to the problem. So this is what an analyst would see in our UI. I haven't done justice to our designers. This is something I have created. what we will see in our traceable platform is something much better than what I'm showing over here. But the idea is that you'll see anomalies identified through time for a certain metric. And by clicking on any of these anomalies, these stars show anomalies, you can drill down to which API it's coming from and then understand why that is an anomaly. So if you look further in, you'll see that, okay, this was the predicted value, this was the actual value. These are the bounds of anomaly or degrees of anomaly, and this has exceeded those bounds. So that's why it's an anomaly. So the problem actually boils down to how do we predict what the metric value should be into the future. And the more accurate our prediction is, the more accurate our understanding or highlighting of that anomaly becomes. As I mentioned, anomalies are identified by comparing realized and predicted value at a certain time, and large deviations imply higher degrees of anomaly. And for predicting the value of the metric, we use long short-term memory models or LSTM models from the deep learning framework. And I'll spend some time on why we are using LSTM models. One of the main, there are three good reasons. One of the reasons is that by using LSTM models, we can use one model to predict the metric for multiple APIs. So let's say, for example, our customer environment has 100 APIs. If we use some other technique, for example, seasonal autoregressive models or SARIMA models, we would have to build one model per API in order to predict the metric values for that API. Using LSTMs, we can actually combine multiple APIs into one model. So we could combine 10 APIs into one model, and we could reduce the number of models by tenfold. The other reason is that LSTM models have a good memory, especially they are very proficient in capturing seasonality. And seasonality plays a major role in the behavior of an API when it comes to understanding its metrics. Some APIs tend to have longer response time, for example, during certain times of the day. That does not necessarily mean that they are going through anomalies. The other vital reason for using LSTM models is that it allows us to use more than the past metric values or the historical metric values to predict what the future values would be. And on the next slide, I'll talk a bit more about this, but this is a very creative way of using LSTM models where we can actually give it more information to predict the values into future. And these variables, we term them as exogenous variables using the statistical notion of exogeneity from like linear regression or ordinary least square regressors. There are some trade-offs of using LSTM models. The benefits of higher accuracy at lower overhead costs, because we have to maintain fewer models, is that LSTM models take a longer time to train. But the argument is that because of their higher accuracy and lower overhead costs, training would not occur very frequently. And even if it does occur, it will not take up a lot of resources. And that's why we envisage that LSTM models will outperform both in terms of accuracy and system usage. So I'll now talk about the exogenous variables and how they fit into LSTM models and why it makes LSTM models very powerful for predicting API metrics. And to do that, I'll use an example of a waiter. And let's say, for example, we want to predict the waiting time of a particular waiter in a restaurant on a certain day. Let's say it's a Friday evening in the month of December, and we want to predict how long is it going to take this waiter to bring out your food after you place the order. So one way would be to look at the historical values of his waiting time. We can look through months and years of data and say, okay, you know, during certain times of the day, he takes longer to bring out your food. During certain times of the month, you know, his performance is different. During certain events like a holiday season, he's more active or less active, so on and so forth. So we could use that historical data of waiting times to predict his future waiting time on a certain day. But we could also do more if we use LSTM models. And one way to see what we could add is things like for the waiter, what was actually ordered on the menu, from the menu. Was it items that require long cooking times, or was it items that require short cooking times? Also, how many items were ordered? Was it a large order with tens of items, or was it just a couple of things that were ordered? Also, what's going on in the kitchen? You know, how many things are actually working? How many utensils are working? You know, is the oven working or is it down? You know, those kind of informations. We could incorporate that to get a more holistic view of what's going on with the waiter's response time or the waiter's waiting time on the order that he collects. This approach cannot be used with things that just look at the historical data of waiting time. For example, as I mentioned, Serema models, they do capture seasonality very accurately, but the inability to add more information makes them not as accurate as, for example, LSTM models to predict how he will perform in the future. So similar to the waiter, the API has certain features that we can use to predict the response time of the API. We could look at how many users are calling the API. What is the structure of the request body? Is it a very large request body or is it a very short request body? How big is the response body? You know, the amount of information that the API is bringing out, how big is that? And also, were there any errors that were experienced during servicing this API request? All these informations, together with the historical performance, historical data of the API's performance, can be combined into predicting the value of the API into the future. So I hope this kind of example adds more meaning into how and why we are using LSTM models. I'll show some production data that we have from some of our customers. Over here on the left-hand side, you see actual API response times. Interestingly, these APIs belong to the same service. And you can see that there's a lot of variability in the response time of these APIs. In order to do prediction, we actually perform some pre-processing of the data before we feed it into the API. With the response time, one thing we do is we move to a smoothened domain of the metric. So essentially, we perform smoothing of the data, and we come, as you see on the right-hand side, into a less noisy version of the data. And then we make predictions on this lower noisy domain, a less noisy domain. And you can see over here that when we predict the values across time, we see that the actual and predicted values visually, I don't even have to show you the metrics. Visually, they are pretty good in predicting where the metrics land up. If we had to do this using this domain or the noisy domain of data, it would be a very poor predictive performance. Once we make the prediction in the smoothened domain, we move back to the actual domain and we do some inverse transformations over there, and we retrieve the original signal, both the predicted and the actual value, and we then compare how large the deviation is, and then we make a call on whether it's anomalous or not. The degree of anomaly is not a binary thing. It's not that yes, it's anomalous or no, it's not anomalous. It shows more it adds a flair of, is it very anomalous? Is it slightly anomalous? So, if you color code it, red would show that there's severe anomaly, amber would show that there's less anomaly, and green would show that it's not anomalous at all. So this is the kind of thing that we look at our end, us at Traceable, to do our analysis. We measure out the true positive, the false positive, and we do a bunch of other sort of machine learning approaches to understanding how it's performing and tune the networks to do better. I'll now talk. Yeah.
Ranaji, quick time check.
Okay.
We do need to leave a few minutes for questions, but if you have some closing remarks.
Sure. Okay. So I'll skip hypertuning. What I will say, though, is bear in mind that we have to develop algorithms that train themselves for our customers. We cannot involve ourselves training models for each customer, for each API. So all this automating requires to be done, so that all we do is launch the algorithm, it looks at the data, it builds the model, it deploys it, and then it starts assessing anomalies. And for that, we also need to perform some hyperparameter tuning, and we use certain techniques to do that in order to do this very efficiently. So I'll stop there. I will open the floor to questions, and I can stop my sharing. Ravi, what would you prefer? Do you want to share your screen, or should I keep mine?
That's okay. We don't need to share screens.
Okay.
There are questions coming in, and Ravi, we should probably answer them live. So the first question is related to self-supervision. Can you comment on self-supervised and how similar or dissimilar it to semi-supervised? Please don't share this.
Oh, can you share it?
Yeah. And I know you also mentioned reinforcement learning, so maybe you can comment on the three, Ravi. Difference or similarities between the three.
Yeah, sure. So self-supervised learning is like it's a new class of algorithms, which you could call as a subset of unsupervised learning. So the idea in self-supervised learning is so when you have supervised learning, what actually happens is you have your target variable and you have your input data, and the goal of the optimizer is to tune the weights such that the error between the input and the expected output is minimized. So that's the goal of the optimizer. Now, in the case of unsupervised, especially if you have closed form networks such as an autoencoder, what actually happens is you need for the optimizer to work, you definitely need an input and an expected output for which it needs to optimize. So that's the fundamental requirement if you have an optimizer. Now, in self-supervised learning, what actually happens is it's pretty much like an autoencoder, but instead of the input being optimized for the input itself, as it would happen in an autoencoder, the input would be forced to optimize for certain variants of the input or certain subsections of the input. So, so if you look at our API data, right? So when we pass certain features into as the input, there are certain subsets of the features which we would kind of optimize for, not the entire feature set, but only for some subset of the features. So that way, the learning algorithm kind of builds something like a supervised model, but it's actually unsupervised. So there's nobody giving you labels. So that's the catch.
Great, and that's self-supervised, right? And reinforcement learning?
Yeah, so reinforcement learning is a completely different class of algorithm. So you would have heard of supervised learning, unsupervised, and reinforcement learning. So reinforcement learning is kind of motivated by the way we humans learn. Supervised learning is definitely not a representative of human learning. So in reinforcement learning, it's hard to explain, but we can explain with an example. So imagine you are crossing a busy street, right? So when you're crossing a busy street and you're crossing for the first time, so how would you actually cross? So what are the estimates that you're making? You're making estimates on how fast the vehicle is moving towards you. You're making estimates on how much of distance you need to cover, and you're also making estimates on what kind of risks are there, what kind of roadblocks are there, and so on, right? So in reinforcement learning, what actually happens is there is an objective function where we have the concept of risk, and we have and we have the goal, which is to reach onto the other side of the road. So a trade-off between the risk and the approach which you would take to reach onto the other side of the road is modeled as a mathematical feedback function. So we have this class of algorithms called policy iteration and value iteration, which is basically going to predetermine the steps that you take in order to reach your ultimate goal, assuming you understand the environment in which you're operating and assuming that the risks are known. So it's hard to explain reinforcement learning, but it's like very different from supervised learning. So in reinforcement learning, we have two classes of algorithms. One is called model free and the other is called model based. So model free algorithms are, I think those are algorithms which came up way back, and they are theoretically sound, but practically kind of impossible. Whereas the model driven algorithms lend yourself closer to the supervised learning paradigm, but they are not fully supervised learning. So imagine something like this. So you imagine you have an algorithm that needs to explore different API calls, and when exploring those API calls makes a mistake. And when it makes a mistake, it gets a negative reward, and it comes back and then explores a different path in the graph. Compare that to an algorithm that can explore the paths based on some other factors, such as the risk scores that we talked about. So the risk scores is giving you some model, whereas in the first case, it was purely model free. So it's kind of a different kind of a learning paradigm.
Great, and we are going to take one last question, which is for Ranaji. In the LSTM model, how do you clean the data before the model can make sense out of it?
Yeah, so what we do is we apply smoothing of the data, which is we use averaging across a time window. And this is a moving time window. So essentially what we do is at a certain point in time, we look at the historical values, let's say 5 minutes ago, and we compute the mean. And that creates a smoothened value of the signal that we are trying to predict. On the other side, after making the prediction, we inverse transform this, and we use a certain technique to do that. And essentially that allows us to go back to the original domain.
Excellent. And Ravi, one more question related to reinforcement learning. What do we consider to be an environment, and what is the action that Traceable takes in that case to get feedback?
Yeah, it's a good question. So we talked about user behaviors, right? We showed you the API call sequences, correct? So the API call sequences, the graphs that you see, that forms the environment for us. So that is the environment that you have observed. Now we can extend the environment by looking at the API spec. So we have something called as the API spec, where we automatically determine What is the, so if you've heard of Swagger, you would have seen an API spec, but imagine Traceable's API spec as an approach where machine learning algorithms figure out the spec for your APIs based on data. Now the specs act as additional information for you to expand your environment. So environment is nothing but adding new nodes into the graph with a very with an educated guess, and the educated guess is driven by the trust scores, the risk scores, and the mathematical model.
Great. Sounds good. Thank you for staying with us. It's been a very interesting hour. And thank you, Ravi and Ranajit, for sharing a little bit more about the technology.
Thanks, guys.